So today we're going to talk about conjugate acid-base pairs, and they're always in pairs. It really is as simple as if you take an H away from an acid, you make its conjugate base. If you add an H to a base, you make its conjugate acid. So let's look at ones you've definitely seen before. So we're going to use the Bronsted-Lowry method of proton moving around. A proton was donated to water. That makes this the acid and this the base. What remains after the proton was donated is the conjugate base. The base that got the H pluses, that becomes the conjugate acid. If you want to think of it a different way, if you go back the other way, the acid always donates the proton, the base always accepts the proton. This acid and its conjugate base are considered a conjugate pair. This base and its conjugate acid are also a conjugate pair. HF and F- are a conjugate pair. You got HClO4, H2O, proton gets donated to water, acid, base. This is the conjugate acid, this is the conjugate base. You could also say, oh look, this is happening, and that's where you get that H plus from if you wanted to make sure you got the acid base right. The conjugate pair in this case is HClO4 and ClO4 minus. You could also list water and H3O plus. For C, how did NH3 become NH4? Well, it gained a proton. That makes this the base and this the acid. How would NH4 become the base? It would donate a proton. So this is the conjugate acid, conjugate base. So you have your pairs. NH3 and NH4 plus are a conjugate pair. H2O and OH minus are a conjugate pair. Notice water in both of these cases is acting differently. Remember, it's amphoteric. And then finally, this is going to be an acceptor, so it is a base acid. This is what's there after it's accepted, so it is a acid, and this is a base. So CO3 2 minus and HCO3 minus are a conjugate pair. Okay, so every acid has a conjugate base, and the conjugate base is what remains after losing the H plus. So HF and F minus. So this is the acid and this is its conjugate base. You need to be able to pick out those pairs. A base has a conjugate acid. The acid is what is made from a base when it gains an H plus. So NH3 gained and became NH4 plus. So this is the base and its conjugate acid. We actually just say, hey, look at this conjugate acid-base pair. So we need to be able to identify a conjugate base from its conjugate acid or a conjugate acid from its conjugate base. So let's practice that here. We're being told that HSO4 minus is the conjugate acid, so we need to come up with its conjugate base. The conjugate base forms when the conjugate acid loses an H plus. And what's important is we're saying one H plus. So we lose one H plus, we get SO4 2 minus. The next one is weird. OH minus, and it's going to lose an H plus or proton, that becomes O2 minus. That's really not going to be happening that much, but okay. The next one is H3PO4. Remember, 1. We lose one proton, so it's H2PO4 minus. We've lost one proton. So the acid is H3PO4. Its conjugate base is H2PO4. What's interesting is we can actually come over here and say the conjugate acid is H2PO4 minus. Its conjugate base is HPO4 2 minus. And we can do it one more time, right? So keep that in mind, especially with these polyprotic acids. The next one, carbonic acid. We're going to lose a proton, HCO3 minus. It becomes bicarbonate. Well, bicarbonate can lose one and become this. So let's go the other way. If people are saying that carbonate is your conjugate base, the conjugate acid forms when the conjugate base gains an H+. So HCO3 minus. Notice that connection. So just to kind of show you, H2CO3 goes at equilibrium with H+, HCO3 minus, HCO3 minus goes in equilibrium with H pluses and CO3 2 minus. So you've got a double equilibrium here. The first Ka value is going to be much higher than the second Ka value because this guy right here, that's the conjugate base and then becomes that conjugate acid for the next one, it controls a lot of this equilibrium. Last one, HSO4 minus. So remember the conjugate base gains an H plus to form that acid. So H2SO4, and of course the charges have been changing because we've been adding or subtracting a proton. So let's talk about these conjugate acid-base pairs and their relationship to Kw. First, this is something you're very familiar with. Weak acid goes in equilibrium and forms H pluses and A minuses. And here is the equilibrium expression, the Ka values. What we're working our way towards is this HA produces the H pluses and A minuses. If HA is weak, then A minus is able to react with water, again equilibrium, and this is not a huge reaction by any stretch, but it accepts a proton from water and you reform HA and you O minus. This time we have a Kb value because it's a proton acceptor. So we have Ka and Kb. If we rearrange these, we can actually sub them into this Kw expression. So let's do that very quickly. Kw is equal to, so rearrange for H plus, we wind up with Ka times HA over A minus. So this is basically the H pluses. Let's do the OH minuses. I guess I don't need the brackets, but when we rearrange, we get Kb times A minus all over HA. I guess I should say I rearranged for the OH minus. When I come through and get rid of all the nonsense, it turns out that the Kw is equal to the Ka, the original acid, and the Kb of its conjugate base. And of course we know at 298 Kelvin, 1 times 10 to the negative 14 is the Kw. And we have another situation where we could say pKw equals pKa plus pKb. So we have a couple different ways of looking at this. So really, what is this weak, strong thing, and what's it have to do with that conjugate base or even conjugate acid reacting with water? First, let's start with a rule. The stronger the conjugate acid, the weaker the conjugate base, and vice versa. So HCl and Cl minus. HCl is the conjugate acid, Cl minus is the conjugate base. The conjugate acid is very, 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 very strong. The conjugate base is very, 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 very weak. That should make sense. In just mathematical terms, if this number is extraordinarily big, then this Kb value has to be extraordinarily small. So it's really kind of a balancing act. Let's look at acetic acid. You wind up with acetate and H pluses. The Ka is 1.8 times 10 to the 5. How strong the acid is. Okay, well, it is weak, but you know, it's the negative 5 out of negative 14. So that gives you an idea of where we're going, because this conjugate base will react with water, reform that acid, and have OH minuses in the mix. And that's basic, isn't it? Kb, with the math and all that fun, 5.56 times 10 to the negative 10. And this is how strong the base is. These numbers indicate the amount of dissociation into the ions, or the amount of reacting, in the case of the conjugate base, with the water. So very little actually reacts with the water to reform the acid, but some does. So let's look at this strength continuum. Let's start at the top here. Strong acids, like HCl, have a very, very, very large Ka value, which means their Kv value is very, very small. Remember, Ka times Kb equals Kw. So if you have a very large Ka, your Kb has to be very, very small. The conjugate base of HCl is Cl-. It is considered ultra weak. My words, not necessarily the words of the people. Let's go to the other side. If we have a strong base like NaOH, its conjugate acid is Na+, its Kb value is very, very large, therefore its Ka value approaches 0, and it is ultra weak. And the important thing about these ultra weak conjugates is they will not react with water. So really our focus needs to be on these in the middle. And I picked one that actually, interestingly, had the same numeric value for the Ka and Kb. So let's go with it. And then I'll add another one. So acetic acid has a Ka of 1.8 times 10 to the negative 5 and a Kb of 5.6 times 10 to the negative 10, and its conjugate base is this acetate ion. So let's look and see what that looks like. So let's see, CH3, COOH goes in equilibrium with CH3, COO minus plus H plus. Well, then that CH3, COO minus, will gain a proton from water to reform the CH3, COOH and actually leave OH minuses. So some OH minuses. The Ka value of this first one is 1.8 times 10 to the negative 5. The Kb value, and we got this by dividing 1 times 10 to the negative 14 by 1.8 times 10 to the negative 5, is 5.56 times 10 to the negative 10. So this is very small. It's not really favored. It does happen, but it's not a favored reaction. Conversely, same situation. If your conjugate acid is NH4, that means your conjugate base is NH3. NH3 making this conjugate acid is favored. Its Kb value is bigger than its Ka value. So let's look at one more, and that's benzoic acid. So benzoic acid, remember benzene and another carboxylic acid. We're going to lose that proton. So we go into equilibrium with benzene C minus plus H plus. Its Ka value is 6.3 times 10 to the negative 5. The question is, what is the Kb value of this guy? That's the conjugate base. This is the conjugate acid. This is weak. We know it's weak because it's not one we memorized. It also has a Ka value. So let's see, Kw is equal to Ka times Kb. 1 times 10 to the negative 14 equals 6.3 times 10 to the negative 5 times Kb. And that gives us a Kb of 1.59 times 10 to the negative 10. So that's telling us about the strength of that conjugate base, and this Ka value is telling us about the strength of the conjugate acid, or in this case, it's the acid we're using. This information is going to come in handy when we start looking at the pH of salts. So, for example, sodium benzoate, which is a preservative, so sodium benzoate looks like this, but, better. Negative. And sodium's that positive counter ion. So, sodium benzoate, what's the pH if you dissolve this in water? It's not 7. It's a salt, but what we have is we have the conjugate acid of a strong base. We know that if your base is super strong, your conjugate acid is weak, so therefore weak. This is the conjugate base of a weak acid, and that's very important because the conjugate base of this weak acid, or any weak acid, will remove a proton from water and create OH minuses in the solution, which makes the solution basic. We're going to start talking about that next time.